Hello everyone and welcome back to the Edmund Optics Imaging Lab. I'm your host, Nick Sishka. If you're just joining us, in our first lab we covered working distance and focal length basics. So we talked about our focal length and field of view and working distance of two different lenses and how their performance compared. The big takeaway from that lab, in case you missed it, is that in general, if you're trying to maximize the performance of your system, you're going to want to try to get a working distance to field of view ratio of around 4:1, which means that if you're looking at an object that's about 100 millimeters in size, you're going to want to try to be about 400 millimeters away. That'll give you optimum system parameters, and it's going to make sure that your system functions in the way that you want it to in terms of costing the least while performing the best. So before I jump into what we're going to be doing for this particular lab, I want to spend a little bit of time with just some quick housekeeping stuff in case you're just joining us. I am not doing these live right now on the air. These are pre-recorded. I am doing the demos real time, so everything that is happening is real. There's no magic or anything happening there. So please bear with me in case there's any minor mistakes or things that I have to tweak. That's part of the fun with all of this, right? As well, I am still standing by and actually able to answer your questions live. So I'm online right now. So if you put in any questions in the chat, I'll be able to answer those questions for you live. I also have my colleague Jay on the line, and he is also an optics expert, and he'll be answering questions as well. So please feel free, drop a line if you have any questions or just want to say hi. So we'll go ahead and get started, launched into this second demo here. This demo is going to be all about lens types and resolution and sensor coverage. So we're going to build off of a little bit what we talked about in the first demo, and we're going to introduce the concept of the camera here. And I know we obviously had a camera in the last demo as well, but in this one we're really going to focus on how the number of megapixels can actually impact your overall system resolution and how you can best manipulate that with the right choice of optics. And so what I have for a setup here is two different cameras, both from Lucid Vision Labs, and I also have a backlight from Metaphase Technologies. And I'm using the same targets that we used in the last lab. These are just glass targets that have stars etched onto them, and we'll zoom into those and check them out a little bit later. Essentially, there's a repeating pattern of stars on there, and as you get closer to the center of each individual star, the resolution linearly increases. So let's talk about a little bit more about what we actually have on here. We have this Lucid Vision Labs Atlas camera. This has the IMX342 sensor in it. This sensor is a 3.45 micron pixel size APS-C format sensor. That means it has a 28 millimeter diagonal on the chip size, and it's 32 megapixels. The little camera that we have down here is the Lucid Vision Labs Phoenix camera. This has an IMX304 in it. That is a 1.1 inch sensor format, and it has a 3.45 micron pixel on it as well. So you'll notice the pixel size between these two cameras is the same. That's actually going to be important for one of the things that we're going to cover during this demo. I'll make sure to bring that point back up later. This sensor, it has a diagonal of 17.6 millimeters, so it's much smaller than the 32 megapixel sensor here. And when you're first going to start a machine vision application, right, the choice could come up. Which of these two cameras should I pick? Should I pick completely different cameras? Should I pick something with smaller resolution or higher resolution? And there's so many different options that are out there from a camera perspective, it can be difficult to make your choice, right? And even once you do choose what type of camera you want to use, the next question is, well, what kind of lens do I want to use? There's hundreds and hundreds of lens options that are out there, right? I have a whole bunch of different lenses that are up here on the top of this computer, and I'm going to pick on a couple of them actually right now, kind of to highlight a few things. This first one is actually well, both of these are 12 millimeter focal length lenses. This is a 12 millimeter, 12.5 millimeter actually, M12 lens. And so these are used for lightweight applications or small applications. Kind of makes sense. It's a small, lightweight lens. So they're used a lot in drones or in document scanners, biometrics, things like this. They're pretty high resolution little guys, but as you can imagine, they're relatively feature simple. They don't have any sort of iris adjustment. You focus them by threading them in and out of their barrel. And there's no real way to lock it down. And so this particular lens is used for, again, smaller applications where you're generally going to be doing a large amount of something or trying to keep that weight down. Your more typical or traditional type of machine vision lens looks something like this. This is also a 12mm lens. This is a high resolution lens designed for a 5 megapixel sensor. It's designed for a 2/3 inch sensor. That's the big difference between these two lenses, is that this lens here is designed for a 2/3 inch sensor, and this other one is designed, the small M12 lens is designed for a 1/2 inch sensor. And it's really the design of the sensor size that determines the size of this lens, and one of the reasons why they're so much differently sized. And so if you're going to pair that lens with a particular camera, that's one of the first specifications that you'll want to look at, aside of course from its resolution and distortion specifications, things like this, is can it actually cover my camera? And you'll want to look at that particular specification on a lens, which is generally notated as something like maximum sensor coverage or maximum sensor format, something like this. And then the number that's used there is some sort of fraction of an inch usually. So you'll have a 1/2 inch or a 1/1.8 inch or a 2/3 inch. The list goes on. It can also be something like an APS-C format, which is what this camera is. So in some cases, they're not necessarily fractions of an inch. And so that's what we would put on our lens spec sheet and to say that, hey, this covers that 1 inch. Now, if you look at what the actual nominal dimensions are on a 1 inch sensor, they're 6.4 millimeters by 4.8 millimeters, and it has an 8 millimeter diagonal. Now, I'm pretty decent at math. I'm not the best at it, but it is impossible to make any of those numbers correspond to a 1/2 an inch, right? So it's actually an old notation that comes back from imaging on tubes. I'm not going to dive into too much of those details there. Shoot us a question if you want to know some of those details. But essentially what we do is we look at the diagonal of that sensor, which in the case of a 1/2 inch is an 8 millimeter diagonal, and we match the lens to that diagonal. Because when we design lenses are obviously round, right? Which means that they output images that are also round or circular. And that means that we need to be able to make sure that the sensor that we're designing the lens for will fit inside what we call our image circle. Now, most of the time you won't hear the term image circle outside of the optics realm, really, but you can see it sometimes, especially if you're using line scan sensors or something like this. You might be able to spec a lens with respect to its image circle. But as I mentioned, this M12 lens is designed for a 1/2 inch sensor, and I want to actually take a look at what happens if I were to get this lens and put it on this 1.1 inch sensor here. So I'm going to get my adapter to C-mount. I'm going to thread this lens in here. Okay, you're going to bear with me real quick as I'm going to have to focus it. All right. So I have this roughly focused. The focus probably is not perfect on here. That's not really what I want to focus on right now. What I want to really look at is just how dark these corners are, right? Most of this image is actually quite dark. And that's coming from the fact that there's a mismatch in what this lens is designed for versus what it is on right now on the camera. So you generally wouldn't want to use something like this, but I really wanted to highlight how a mismatch in your sensor size with your lens can create major problems for your imaging system. So now I want to take the other 12 millimeter lens, which again is still not quite designed for the 1.1 inch, and I'm going to put it on here. Same exact field of view. We're going to actually have basically the same angular field of view here, and that's because the lenses are the same focal length. So we're going to get actually a very similar looking image, except for the fact that our corners are much less dark here, right? And this is one of the interesting things about lens specs and things like this, is that if you were to just look at a spec table from this M12 lens and this C-mount lens here, there probably wouldn't be too many differences, except if assuming there wasn't an image of the lens on or something like that that showed dimensions. But one of the things that you would actually see is the sensor coverage, of course, being different. And you can see how this one that is on the camera right now that covers the 2/3 inch sensor has a much less of a dark area that's on there. And one of the ways that we can dive into detail on that in a lens spec sheet is using what we call a relative illumination curve. And the relative illumination curve is going to plot our relative lens brightness from the center of the image all the way out to the corner of the image, which is really saying what's the brightness along a particular image radius, right? Because we have the diagonal, which would correspond to our overall image circle diameter, right? So that's radius then, of course, being half that diameter. And what we can see if we look at a plot like that is just how much that brightness tends to tail off. And so in most cases, you probably wouldn't want to use this particular lens on this particular sensor because, again, you see those dark corners. But there are some instances where you might want to. Let's say you're looking at a bottle cap or something that's round. And so you don't necessarily need to have the corners in view, but you need that extra height and a little bit of extra width in order to see the full image there. So in this particular case, you could use your relative illumination curve and say, well, hey, I know that I'm actually not going to be using much beyond the 2/3 inch diagonal position, but I do need that extra horizontal and vertical. Now, what the relative illumination curve isn't going to tell you is what the overall system illumination is going to be like. There's some things that go on within the sensor itself from micro lenses and also software correction and gain correction that can actually change what this looks like on an overall system level perspective. So I'm actually going to hand this over right now to Mike Jacoby from Lucid Vision Labs, and he's going to talk to you guys right now about sensors and some of the new developments that are coming. Mike, it's all yours.
Hi everyone, I'm Mike Jacoby from Lucid Vision Labs, and I'm here to talk about newer, higher resolution sensors and how they impact the machine vision camera design and what features you need to look out for in a camera so that you're getting the most out of that awesome, newer, higher resolution sensor. It can be very beneficial to move up towards a higher resolution sensor. There are a couple reasons for this. First off, higher resolutions allow you to simplify your application design by reducing the overall number of cameras needed. For example, instead of using 3 or 4 or 5 megapixel cameras, you can maybe use just one 20 megapixel camera. This of course also has a domino effect on the reduction of camera accessories too, less lenses, less cables, potentially even less lighting. Not to mention a reduction in maintenance over the lifespan of your application. On the other side, say you choose to keep the same number of cameras but upgrade to a higher resolution, you can speed up inspection by imaging a larger scene, placing more targets to be inspected in the field of view at one time. Typically, higher resolution sensors, let's say 12 megapixels and up, are going to be larger in their sensor size versus lower resolutions. And what we've seen over the past couple of years is a growing number of new sensors moving beyond the 1-inch sensor size. We see sensor sizes at 4/3 and beyond. For example, the 31.4 megapixel IMX342 on the Atlas camera is an APS-C size sensor, which is larger than 4/3. If we even look at some of the latest 4th generation Sony Pregius sensors, even though their pixel size is smaller than their 2nd and 3rd generation, they're still packing in a high number of pixels. The 24.6 megapixel IMX530 sensor on our Atlas 10 camera is a 4/3 type sensor size. Improvements in pixel technology has allowed for pixel sizes to shrink, but still retain similar image quality performance as larger pixel sizes. Overall, we're seeing a trend in both pixel sizes getting smaller and sensor sizes also getting bigger. Obviously, sensors don't just work on their own, and they need to be properly integrated into the camera. So is it enough to just get any camera with these high resolution sensors? Well, not necessarily. Here's what we do at Lucid to maximize image quality. First off, integrating these larger sensors takes more expertise to ensure maximum image quality, because larger sensors can be more sensitive to back focal distance tolerances such as tilt, rotation, and centering in relation to the lens barrel. So it's very important that sensors are precisely placed in the camera, as well as also being consistently placed correctly between each unit, so that each unit performs predictably from one to the other. A slight sensor displacement of 30 micrometers in edge tilt can mean that while the center of your image is looking sharp, your corners are blurry. At Lucid, all of our Triton and Atlas models employ active sensor alignment when the sensor is placed into the camera. This manufacturing step aligns the sensor actively during its placement by making very precise adjustments in real time as it calculates the maximum sharpness across the entire sensor plane. Once that calculation is made, it will fix all the imaging components in place. This ensures clear, sharp images from the center to the edge of the image. Second thing that's important is making sure the camera goes through proper sensor clarity tests after manufacturing. For all of our cameras, we do robust testing to check for hot pixels and darker defective pixels at various camera temperatures, as well as dust particle inspection on both sensor and camera glass. Other important testing is the ENVA 1288 sensor performance tests. This standardized testing measures image quality specs such as quantum efficiency, dynamic range, saturation capacity, and more. These tests measure the sensor's performance inside the camera, so they take into account cover glass, if any, and any impact surrounding camera components and circuitry might have on the sensor, and therefore offer a more realistic performance number than if you simply just relied on sensor specs alone. At Lucid, we not only do thorough pixel testing on each unit, but we also perform ENVA 1288 image performance testing and offer that data online so you can better compare camera models. Finally, we also allow for shading correction. This helps correct for darker edges in the scene. This can happen because with larger sensor sizes, there can be a tendency to have less light transmission near the edges as we move away from the center of the sensor. This is partly to do with the quality of lens you choose for sure, but it's also because the tiny micro lenses that sit on top of each pixel, their shape is the same for each pixel. So for pixels that sit farther away from the center, their micro lenses are not shaped differently or tweaked to better capture the light that comes in at a steeper angle. So shading correction can be used to calibrate a gain boost in the edges for more uniformity across the image. All right, those are just a few things on how higher resolution sensors can benefit you, how they affect camera design, as well as some of the things that we do to maximize quality performance in larger sensor sizes in our cameras. Thanks for watching.
Thanks so much for that, Mike. That was excellent information. So while Mike was talking with you guys, I actually took the liberty of changing around my setup a little bit, and I actually moved up the 1.1-inch camera, the 12 megapixel camera, and I put a different lens on. And I want to actually start diving into how those megapixel changes can actually have an impact on a system. I think most of us are familiar with going to smaller pixels, but what happens if you blow up your imager size and keep your pixel size the same? And I mentioned back at the beginning of this lab that the pixel size in both of these cameras are the same, but the sensor sizes are vastly different. The diagonal on the 12 megapixel sensor is about 17.6 millimeters. The diagonal on the APS-C format sensor is about 28 millimeters. So there's a big difference, about a 10 millimeter difference between the two between the two sensors, excuse me, on their diagonals, which means you can cram a whole bunch more pixels, right? We only have 12 million pixels here, and we have 32 million on the larger camera there. So what does that actually correspond to from an image side of things, right? From a lens side, we have a 50 millimeter lens on the 12 millimeter camera, and we have a 75 millimeter lens on the 32 megapixel camera. And the working distances, you'll notice, are about the same, right? There's maybe a few millimeters different, but they're functionally the same, and we're looking at the same size field. So in this particular case, we're looking at this 4-inch, about 100 millimeter horizontal object. These are these star targets. And I want to take a look at what actually happens now that we have different megapixel counts. Because we have the same field of view, but we have different sensor sizes, our magnifications are actually different. The magnification in this system, on the 32 megapixel system, actually is higher. And how does that correspond to a different image? Well, let's take a look at this. Let's zoom in on some of these. So this imager on the right here is the 12 megapixel. So we're going to zoom way into the center, about this far. And what I want to do is start looking at these star patterns. And you can see as the resolution comes in and gets higher and higher and higher, as this radius gets smaller, we slowly start to lose our resolution until it eventually bottoms out. Let's see how that compares to the 32 megapixel image. So I'm going to do the same thing and zoom in here to about the same size. And you'll notice right away that the stair-stepping effect here that you're getting from the features on the star target not quite aligning with the alignment of the pixel size is much different. You're seeing it much smoother on the 32 megapixel imager than you are with the 12 megapixel imager. And as you start to step into the center of the target, you're actually able to see much farther with the 32 megapixel imager than you are with the 12 megapixel imager. And that is simply because you are having a higher magnification, which means that each individual pixel is actually taking up less space from an object perspective. And what that means is that you're going to get a smoother image, and you're actually going to be able to view smaller object details, even though your pixel size is the same. And This is something that's not oftentimes discussed, which is if you want to go to a higher megapixel count, blow up your image sensor. Generally speaking, if you blow up your image sensor, it tends to grow your pixel size with that as well. In this particular case, that's not necessarily happening, and honestly, this is, in my opinion, the better thing to do in terms of maintaining your image quality and actually getting improved image quality, is making sure your pixels stay as large as they can. When you start to go to really, really small pixels, you can encounter signal-to-noise ratio issues and other things that happen with small pixels that you simply won't encounter with some of the larger pixels. And so in this particular case, the 32 megapixel imager has a much sharper image, and we can see, even as we zoom in a little bit farther, right, really, really close to that center, maybe one more out here, we can really start to see that taking effect. The higher magnification just providing a much better and more crisp image. So quick takeaway from this, don't necessarily think that just because you want to increase your megapixel count that you should go to a smaller pixel. Your smaller pixel could present all kinds of other issues with this particular setup, and overall staying with your larger pixels is going to give you better image quality. Thanks so much for sitting with me during this lab, you guys, and see you in a few minutes.